as a corollary of our theorem. Suppose f is continuous in the interval and minus pi equal f pi. Then for any epsilon positive, there is a trigonometric polynomial Trigonometric polynomial is the linear combination of finite linear combination of sine kx and cosine kx, k from 1 to some n, okay? As such that f minus g, we introduce the infinite sum norm. The definition is x in minus pi fx minus sx less than epsilon. That is, for a continuous function defined over minus pi to pi, you can all assume that this continuous function has the same value at the end point of the interval. Then you can find the trigonometric polynomial as close as you want to the function. Okay? Given any epsilon positive, you can find the as close as possible as you want to the f. So the closeness is described by this norm, by this infinite norm. This norm I will introduce to you here. Some remark. Suppose f is a function defined over AB interval, bounded function. Then we defined. We don't require f to be continuous. It just need to be bounded. Okay. Then we denote this to be the supernomen of the absolute value of fx when x go over AB. So this is a very useful notation. The L infinity norm is very useful. For example, suppose we have a sequence of functions. Then Fn converge to F uniformly. If and only if the L infinity norm of Fn minus F goes to 0. I remind you that this L infinity norm is a sequence of real numbers, a sequence of non-negative numbers, right? Because the L infinity norm of a function is a numbers. So for every n, you have a number. So you have a sequence of number. So you transform the uniformly converging problem into the convergence of a sequence of real number. Therefore, this makes it very convenient. Okay. So this corollary says that any continuous function can be approximated by a sequence of trigonometric polynomial. In other words, taking epsilon to be 1 over k, and for every epsilon equal 1 over k, the corresponding s denoted by sk, then you obtain a sequence of trigonometric polynomial sk, which converge to f uniformly. Okay, converge to f uniformly. So this is very important. Okay, now we shall prove this result. So we know that because f is continuous on the closed interval minus pi. Therefore, f is uniformly continuous. f is uniformly continuous on minus pi. So for any epsilon positive, there exists a delta positive such that if x and y belongs to this interval, and the distance from x to y, that is the absolute value of their difference, is not greater than delta, then fx minus fy will not greater than a third of epsilon. So this is the interval minus pi. So we obtain, for any epsilon positive, we have such a delta. Then we take a partition of the interval. Take partition p xi I from 0 to m of minus pi of this interval. Take a partition such that the length of every subinterval is not greater than delta. This is possible. We take some point, including minus pi and pi, to divide the interval into subintervals. So that every subintervals, the length of every subinterval is less than delta. This is possible when you take in sufficient many point xi. This is possible. Then the function, our function is here. Then using the points, we can construct a function piecewise linear. Construct a piecewise linear. Let G be piecewise linear. Piecewise linear function determined by the partition about P, which means G is the function whose graph is maybe I will we ignore the small red dots. Ignore them. We only I don't want to work with so many points. So the graph of G, just take a corresponding point on the graph of F, and then link them with segment. Oh, sorry. So this is G. The blue one is our F. So you have partition. You have a partition of F of the interval. Then you take the corresponding point on the graph of F. You obtain the point. Then you connect the points on the graph of F. This is the graph of a so-called piecewise linear function, determined by the partition P. That is the P is obtained the graph of P. Graph of G are obtained by connecting the points xi, fxi. This is the what we call piecewise linear function. Of course, since f pi equal f minus pi, we also have g pi equal g minus pi. Obviously, this is true. And we also know that the f for every x in minus pi, we must have fx minus gx not greater than a third of epsilon. Why this is true? Because, for example, because x belongs to the interval, there must be some I such that x belongs to xi minus 1 xi. Then because gx is linear, the graph of gx is a segment. For example, this segment. Okay. So and the maximum fx and fy in this interval is not greater than a third of epsilon. So you can see that gx, the difference from gx to fx must also not greater than epsilon over 3. Okay, so this can be proved not difficult, but it is a little time consuming. I will omit this. Okay, this is an easy task. So let Sn be the partial sum of the Fourier series for the 2 pi extension of g. G is defined over minus pi in this interval, but we make a 2 pi periodic extension of g, and we still denote it by g. Okay. And the partial sum of the Fourier series, of g, the 2 pi extension, actually the 2 pi extension of g, we have what? We have Sn minus g less than half of epsilon if n is large enough. Okay, because g is piecewise differentiable. G is piecewise linear, of course piecewise differentiable. Now using our previous theorem, this theorem says that for piecewise differentiable function, the Fourier series converge to the function uniformly. Okay, now our g here is piecewise linear, of course piecewise differentiable. So the Fourier series of g converges to g uniformly. That is, the partial sum converges to g uniformly. As I explained when I introduced the infinite norm, this is equivalent for the infinity norm of the partial sum n g goes to 0. So when n large enough, it will not greater than half of epsilon. Okay. Now our fn, the infinity norm of f minus Sn, of course will not greater than f minus g plus g minus Sn. But g minus Sn already less than half of epsilon. For f minus g, because for every x in the interval minus pi, the absolute value of fx minus gx is not greater than a third of epsilon. So the supplement of this is precisely the L infinity norm. So every x, this is not greater than a third of epsilon. So the supplement will not greater than a third of epsilon. So this sum, in conclusion, this sum will not greater than a third of epsilon plus half of epsilon. Of course, this is less than epsilon. Therefore, we have found the trigonometric polynomial Sn. The L infinity norm of f minus Sn is less than epsilon when n large enough. This prove our result. Prove our corollary. The continuous function f can be approximated using trigonometric polynomial s. That is the here is s. Sorry, I have misprint here. Minus also minus s. So the L infinity norm of f minus s is less than epsilon. Okay, so we have achieved this goal because in our this argument we eventually obtained when n is large enough, f minus s and L infinity norm not greater than epsilon. So proving